In the early 1930s, Admiral Richard Byrd returned to Antarctica. His first expedition had ended a few years earlier, and the base camp at Little America, along with everything they'd left behind, had been swallowed by the ice shelf. When his crew dug down through the snow, they found equipment from the original mission still buried in the frozen ground. Among it, a set of Kohler generators, the same units that had powered the camp's lights and radio. The casings were frosted white. The fuel lines had gone stiff. These machines had spent years locked in temperatures that would kill most engines long before anyone tried to start them. But according to Kohler's own corporate history, the crew hooked up a battery, hit the starter, and the generators fired on the first attempt. Kohler used that story for decades. Byrd himself was so impressed that he named an Antarctic mountain range after the company. But the story raises a question that matters far beyond marketing. Cold destroys engines. Oil thickens into something that fights the starter motor, while diesel fuel crystallizes into wax that clogs the lines before it ever reaches the combustion chamber. At the same time, the battery is losing the cranking power it needs most. And below a certain temperature, even gasoline stops producing enough vapor to ignite. These failures don't arrive one at a time. They hit together, and when they do, the engine doesn't struggle. It simply doesn't start. So how did those generators survive? To understand what cold actually does to a generator, you have to look at the fuel first, because each fuel type breaks down in its own way, at its own temperature. Diesel is the most vulnerable. It contains paraffin wax, which stays dissolved as long as the fuel is warm. But as the temperature drops past about 32 degrees Fahrenheit, that wax begins to crystallize. The fuel turns hazy. Engineers call this the cloud point, and the tiny crystals start collecting in the fuel filter. Drop another 15 or 20 degrees, and the diesel reaches its pour point, where it thickens so much it stops flowing entirely. The cetane number of the fuel affects how cleanly it ignites once it does flow, but if it can't flow at all, that number is irrelevant. At that point, the engine is starved. This is the failure mode you see most often in commercial diesel standby units. The Cummins and Caterpillar sets that back up hospitals and data centers, because they sit idle for months between tests, with fuel that's had time to degrade. Gasoline has a different problem. It doesn't gel, but it has to vaporize before it can ignite, and cold air suppresses that process. Refineries compensate by adjusting their formula seasonally. Winter blends are loaded with extra butane to make the fuel more volatile. A generator sitting in a shed with 6-month-old summer blend fuel is fighting chemistry it was never designed to overcome. The portable generators most homeowners rely on, the Briggs and Stratton units in the garage, the Honda inverter generators people buy for camping, are the ones most likely to fail this way because they're gassed up in August and forgotten until December. Propane seems like the safest option because it doesn't degrade in storage. But its boiling point is minus 44 degrees Fahrenheit, and below that threshold, the liquid in the tank simply stops converting to vapor. The tank reads full, but nothing reaches the engine. Natural gas generators avoid most of these fuel storage problems entirely. The fuel arrives through a pipeline and doesn't sit in a tank. But they're not immune to cold. The regulators and valves that control gas flow can ice up, and the combustion characteristics of natural gas change enough in extreme cold to cause misfires and hard starts if the engine management system isn't calibrated for it. Fuel is only half the problem. Even if the chemistry cooperates, the engine still has to turn over, and that's where cold does its quietest damage. A lead-acid battery loses capacity as it cools, and the decline is steep. At 32 degrees, roughly a quarter of the cranking power is gone. At 0 degrees, the battery is down to about half. The industry measures this with a spec called cold cranking amps, defined at 0 degrees Fahrenheit, because that's exactly where engines are hardest to crank. A battery rated at 750 cold cranking amps at 0 degrees is effectively delivering something closer to 375 amps once thermal losses are factored in, which is often right at the edge of what a cold engine requires. A battery maintainer, or tender, Keeping that battery at full charge over the winter doesn't fix the thermal loss, but it ensures you're starting from the top of the curve rather than partway down it. And the reason they're hardest to crank is the oil. A generator left outside overnight in sub-zero air has oil that's turned sluggish, clinging to every surface inside the crankcase. The starter motor, itself a small but critical engine component, has to push through that resistance with a battery that's already half dead. This is the combination that triggers the most common cold weather fault code on Generac standby units. A battery that reads 12.4 volts at rest but collapses below 10 the moment it tries to crank against cold oil. Those units are typically wired through an automatic transfer switch that's supposed to bring the generator online within seconds of a utility outage. And a failed cold start means the transfer switch trips to a generator that never fired. There's one more failure that catches people off guard because it happens after the engine is already running. Portable generators vent crankcase pressure through a small breather tube. In freezing air, moisture condenses inside and freezes solid, blocking airflow and forcing oil out of the engine. Honda saw this often enough in northern climates that they developed a breather heater kit, a 10-watt coil that fits inside the tube. It ships standard in Canada, but is an optional add-on in the US that most buyers never hear about. Everything that kills a generator in the cold comes down to one missing ingredient: heat. And every engineering solution the industry has ever developed works the same way. It puts heat back into the system before the engine has to start. The simplest fix is the oil. Switching from a conventional SAE 30 weight to a synthetic 5W30 changes how much resistance the starter faces on a frozen morning. Diesel operators in Alaska and northern Canada go further, running 0W40 synthetic year-round. Fuel is the next layer. In diesel country, the answer is switching to number 1 diesel, a lighter blend with far less wax that stays fluid to roughly minus 20 degrees, or adding anti-gel additives to standard number 2. Gasoline generators rely on the refinery to do the work, which is why storing fresh winter blend fuel matters more than most owners realize. Beyond fluids, the solutions get mechanical. Coolant heaters and oil pan heaters keep the block warm while the generator sits idle. Glow plugs heat the diesel combustion chamber electrically before the starter engages. For engines without glow plugs, there's ether, a starting fluid so volatile it ignites under conditions that would defeat any diesel blend, though aggressive enough to damage an engine that already has glow plugs. I think the most interesting part is how old all of this technology is. None of it required a breakthrough. Block heaters have been around for decades, and glow plugs are World War II-era engineering. The physics of cold hasn't changed, and neither has the fix. The only thing that changes is whether someone installs the right hardware before the temperature drops. If you want to know how far cold weather engineering can actually go, the answers are in military technical manuals and at the bottom of the world. The U.S. Army's tactical quiet generators are rated to start unaided down to minus 25 degrees Fahrenheit. That's the baseline. Nothing plugged in, nothing preheated, just a cold engine in cold air. Below that, the winterization kit takes over. On modern sets like the MEP802A, it's a diesel-fired coolant heater that circulates warm fluid through the engine block before the operator touches the starter. With that kit, the rating extends to minus 50 degrees. Older sets from the Cold War era pushed it further. The 30-kilowatt MEP005A carried winterization hardware rated to minus 65. At the South Pole, the Amundsen-Scott Research Station runs 3 Caterpillar generator sets, each producing 750 kilowatts. They burn AN8 jet fuel, chosen because its freeze point is minus 58 degrees Celsius. The more common, JP8, freezes at minus 47, and that margin was too thin for fuel sitting in outdoor tanks at roughly minus 45. The operational rule is absolute. The generators never shut down. At any given moment, a single unit carries the full station load while a second idles on warm standby, ready to take over if the primary trips, and only the third is allowed to go offline for maintenance. A cold start at those temperatures wouldn't just fail, it would damage the engine. That number surprised me. The engineering at the South Pole isn't about surviving the cold. It's about admitting that below a certain point, even the best cold start technology isn't enough, and the only safe strategy is to never let the engine go cold in the first place. Everything in this story points to the same conclusion. Cold weather failure isn't a surprise. It's a known engineering problem with known solutions. The only question is whether anyone applies them before the temperature drops. In February 2021, Texas answered that question. Winter Storm Uri pushed temperatures to -2 degrees Fahrenheit at Dallas-Fort Worth, conditions the state's power grid had never been designed for. The joint investigation by FERC and NERC found that freezing issues caused just over 44% of all generation failures, while fuel problems accounted for another 31%. Together, those two categories explained more than 3/4 of every unplanned outage. Over 1,000 generating units failed to start, and the grid lost 61,800 megawatts of capacity. More than 4.5 million Texans lost power, some for days. The state's final mortality report confirmed 246 deaths, with 161 caused by direct exposure to extreme cold. Generators that had run reliably for years in mild winters simply stopped because no one had installed the heating elements or winter fuel systems that would have been standard in Minnesota or Alberta. Every winter since, grid operators and reliability engineers have pointed to Uri as the definitive case study in what happens when cold weather preparation is treated as optional. And with increasingly volatile winter weather patterns, the lessons keep becoming relevant again. The technology existed. It had existed for nearly a century. Kohler proved that in Antarctica in the 1930s, and the U.S. Army codified it into field manuals during the Cold War. The generators that survived Uri were the ones somebody had winterized before the forecast changed. The ones that didn't were just cold iron.